Welcome to this tiny tutorial on the simply type lambda calculus in Lean. In this tutorial we will discuss a part of Lean that forms the simply type lambda calculus. The simply type lambda calculus can be seen as the core of the programming part of Lean, and it consists of the zero type, the product type, the function type, and the coproduct type or sum type. And these types are all part of Lean, and I will discuss them and go through a few examples in this tutorial. We start with a few imports which are not of relevance to this tutorial. This is to make all the type and term constructions of the simply typed lambda calculus available in this file. The first type that we are interested in is the empty type. In Lean, the empty type is called empty. So when we check empty, Lean tells us that empty is a type. The empty type does not have any introduction rule, so we cannot by default construct a term of the empty type. By default here means without assuming any other hypothesis. However, we have an elimination rule for the empty type, and this elimination rule is called empty.elim. If we check this, then we see that empty.elim is a function from empty into any other type. So here we have a question mark. This means that we can, if we want, plug here, obtain any other type. The reason why this is written in such a weird way is technical. So empty.elim is a function from empty into any other type. We can write this slightly differently with an at here, and if C is a type, then we can check at empty.elim C. This now has the effect that instead of an arbitrary type here, we can indicate we get that this function empty.elim is a function into the type C that we have specified up here. So the C here, this is an implicit argument, and this is why in the previous view, if we go back to the previous view, this argument here corresponds to an implicit argument to empty.elim, and using this at here, we turn this implicit argument into an explicit argument, so we specify it here, and then we see that empty.elim is a function from empty into the type C. This is for technical reasons only and not of importance for the purpose of this tutorial. So we can define a function from empty, which is a function from the empty type into the type C. There is no computation rule because there is no introduction rule for the empty type. The next type we look at is the product type. An example of the product type is the type of n times n of pairs of natural numbers. So the way to write this in Lean, this symbol is \times. We suppose we have two types A and B, and then we know that we can form the product type. Let me write this down here quickly and check that this is indeed the case. So A and B are two types, and then A times B is again a type. Now, for the introduction rule, we suppose having a variable A of type A and a variable B of type B. And with these two terms A and B, we can form a new term, which is the term parenthesis open a comma b parenthesis closed, so the pair of a and b, and this is a term of type a times b. This is the introduction rule. For the elimination rule, we assume we have a variable t of type a times b. We can then form two new terms. The first term is the term t dot 1. It has type a. In Lean, it's actually written as t dot fst, which stands for first. So dot first extracts the first component of t, and t dot first, or synonymously t dot 1, is a term of type a, and t dot 2, or synonymously t dot second, is a term of type b. Now to the computation rule. Here we form the term a comma b dot 1, so we take the a and b given here as variables. We apply first the introduction rule and then the elimination rule, the first elimination rule, dot 1. And if we look at what this reduces to in Lean, well, it reduces to just a. Similarly, if we first use the introduction rule and then the second elimination rule, dot 2, this term reduces to b, the second term of this pair. This concludes our study of the product type in Lean. The function type in Lean, we first look at an example. Here we look at the example n of functions from the natural numbers to the natural numbers. Lean tells us that this is a valid type. We now assume having two types, a and b, and we look at the introduction rule for functions from a to b. The introduction rule cannot really be expressed very well in Lean because we cannot assume that a variable b depends on a parameter in a. So while we can write lambda a in a comma b, we cannot write a variable b that is general enough to depend on a parameter a in a. However, we can do this for examples. For instance, we can look at the function lambda n plus n. Here, n plus n is a term that depends on a variable n, which is a variable of type natural numbers. So here, in this case, this is the term b, and this is the term a, the variable a. In this example, b depends, which is n plus n, depends on a variable n here of type natural numbers. And when we check this term, lambda n plus n, Lean tells us that this is a function from natural numbers to natural numbers. So this n here corresponds to this input n, and this n here is the type of n plus n, which is a term of type n under the assumption that n is of type n. The elimination rule reads as follows. If f is a variable of or a term of type AROB, and A is a term of type A, then F applied to A, which is just written as the juxtaposition, F applied to A is a term of type B. In the computation rule, again, we cannot give a general example since we cannot express if a term B depends on a variable A. However, we can demonstrate computation in examples. Here, we write a function that maps a variable n to n plus n. And we apply this function to an argument here 4. This term, lambda n plus n applied to 4, it reduces to 8. How does Lean do this calculation? Well, it looks at the body of the function, n plus n, and there it replaces all the occurrences of n by 4. So instead of n plus n, it considers 4 plus 4. And 4 plus 4, Lean reduces to 8. This is how the computation rule for functions in Lean works, and actually in any functional programming language. Finally, we have the sum types. Here we have an example of a sum type. The type, so n is again our favorite type of natural numbers, and n plus n is then again a type, a valid type, which is the type of copairs of n. So it's the sum type n plus n, and in Lean this type, the plus is already, the symbol plus is already used for the addition of natural numbers. So in Lean we use instead the symbol called O plus, O for a circle around the plus, to denote the type construction plus. As to the introduction rule, if we have variables a of type A and b of type B, then we can construct a new term of type A plus B. And this is done with the keyword in left and in right. So here we check the term in left of A, and Lean tells us that this is a term of type A plus something, and Lean does not know what the something is. It does not know what B here is. This, we want this to be B, but from the term in left of A, Lean is unable to deduce what B should be. We can solve this by annotating the term in left of A with the type that we want it to be, and then Lean, so we suggest to Lean to use the type A plus B, and then Lean confirms that in left of A is of type A plus B. The problem here is similar to what we've seen before. It's that A and B are implicit arguments to the construction in left, but we can render these, we can turn these arguments into explicit arguments by prefixing in left with an @ sign, and then Lean understands that in left A, B, A is a term of type A plus B. The problem here is similar also to the fact that in the OR introduction rule, we have to write OR.intro PQ, for instance. We have to indicate the proposition that we do not prove if this is supposed to be a proof of P or Q, where Q, this tiny q, is a proof of Q. Finally, let's come to the elimination rule. The elimination rule is called sum.elim in Lean. It is unreadable if we don't give any arguments. So let's look at instead a fully annotated term. So sum elim ABC is of type A ROC to B ROC to A plus B ROC. This means that to construct a function from A plus B to C, it suffices to have a function from A to C and a function from B to C. This is analogous to the OR elimination rule, where in order to prove that A or B implies C, it suffices to prove A implies C and B implies C. The computation rule can be tested like this. We assume having a function f from A to C and a function g from B to C. And then we can form the term sum elim of f and g. So this is now, let me insert here a tiny check. Sum elim fg is now a function from A plus B to C. And if we evaluate this function sum elim fg on a term that comes from A, then we obtain f of A. And if we evaluate this function sum elim fg on a term that comes from B, then we obtain g of B. So this corresponds to a case distinction where when we evaluate such a function sum elim fg on an element that comes from A, we use our function f. In case the argument to this function comes from A, we use f. And in case the argument we apply this function to comes from B, we use g. This concludes our tiny exploration of the simply typed lambda calculus in Lean. See you soon.